In this lecture, we're going to talk about how to balance the redox reactions that we saw in lecture 12. Remember from lecture 12 that a redox reaction is a reaction in which electrons are lost and gained. And some of them can be difficult to balance because they take place in water and they really utilize water molecules in the reaction as needed. And so we kind of had to make a prediction about how many water molecules they'll need in the reaction, if any. And also, they often take place in what is called an acidic solution or a basic solution. And depending on which type of solution it takes place in, that's going to affect your balancing. So we'll look at how to balance those. First, I want to visit what we talked about previous to this in lab. Hopefully we've gotten to this in class, and if not, this will be a good preview. And that is the activity of certain metals. Okay, so we're going to switch to looking at a little simulation here where we're viewing the activity of different metals. And what that means when we say activity is really referring to the reactivity. So some metals are very reactive while others aren't. What we're looking at here is placing a metal in acid. So I'm going to start with the metal tin, and we're going to put it down in the acid, and this is hydrochloric acid. And according to the simulation, you can see there are some bubbles coming off there. So we know that tin reacts with acid. So it must be pretty reactive. Let's look at lead. Place it into the acid. We see bubbles form. You also see that metal getting smaller as though the acid is kind of eating away at the metal. So the metal is reacting with the acid, and that's why it appears to be getting smaller. What's really happening is the metal is forming ions, and those ions are going into the water. So it's not like some magic trick where the metal is disappearing, but it's just dissolving into the water and is being dissolved by the acid. So lead and tin are both reacting with this acid. We'll keep going and try nickel. Also seeing bubbles. And the metal piece appears to be getting smaller. This one appears to be reacting even more than the rest of them. But we can tell that nickel is reactive as well with this acid. All right, let's try copper. Place it into the acid. And we're waiting, just like we did with the others. But nothing ever happened. There's no reaction between copper and the acid. And that is because copper is not as reactive as those other metals. And we say it's less active, is the way that we would say that. So copper doesn't react with this acid. And let's try one more on here, silver. And, oh, sorry, I didn't press start. Oh, yeah, I did. Start. It's asking us to wait. Well, I couldn't tell that I had already pressed start because nothing's happening. So silver also is not active enough to react with hydrochloric acid. And that's good for us because if you think about the uses of silver and copper, so we use them in jewelry, we use copper to coat pennies, etc. If these things reacted with acid, they would be dissolving all the time because we have acids all around us. I mean, vinegar, for example. What if you were cooking and you had on some silver jewelry and you accidentally splashed the vinegar on you? Oh, there goes your necklace. But that's not the case because silver is not active enough to react with hydrochloric acid. So that's why we use those metals more often than, say, nickel or lead or tin in our everyday applications because of that lack of reactivity. However, there are some acids that can cause these less active metals to dissolve, and it's actually through a different mechanism. And one example of that is when you put copper into nitric acid. Okay, nitric acid has a different mechanism of reactivity than hydrochloric acid, and that's what we're going to study kind of in this lesson, is what kind of reaction is going on here, because we saw that copper is not reactive with hydrochloric acid. So what happens when we put it with nitric acid? So that's what we're going to be looking at here.
Alright, what we're doing is we're going to take two pennies. One shiny, and the other one is pretty corroded. And I'm going to separate them here, and then I'm going to pour in some nitric acid. Nitric acid. Ooh, good stuff. Are you ready for this, folks? Here it is. Wow, did you see that really shiny penny went first? But the other penny is reacting more quickly. Oh, there we go. Okay. Now, what you're looking at is the gas that is being produced. That's nitrogen dioxide. And nitrogen dioxide is not nice stuff. That nitrogen dioxide is what you see in smog.
So we're looking at here a reaction between nitric acid and copper, and we see that there is a reaction, unlike what we saw with hydrochloric acid, but it's also different in that it's not these little bubbles like we saw in the previous simulation. Those were producing hydrogen gas. This, on the other hand, is very different. This is nitrogen dioxide, which is a poisonous gas being given off. So we know that something different is happening than, let's go back to the simulation if we can, and look at just 10, for example. Those bubbles that you're seeing there, those are hydrogen gas coming off of the hydrochloric acid. But in nitric acid, something else is happening entirely. So we want to look at that more closely. All right, so moving back to the notes. If we look at the reaction between metals and nitric acid, it's not the hydrogen, the H+, that's doing any of the work in that reaction. In fact, the H+ is a spectator. As you see here, it's not even included in this initial reaction. It's the nitrate, that NO3 ion, that is highly reactive, and it is going to cause that metal to dissolve. So you see here, the reaction is the nitrate ion reacting with the metal to form nitrogen oxide or nitrogen dioxide gas, depending on the concentration. Here they have it as nitrogen monoxide. And then you have X, which is your metal, and now it's in the ionic form. It has been oxidized by the nitrate ion. And what oxidize means, remember, is to lose electrons. So now, instead of it being metal solid, it's got a positive charge, so it's metal ion, and it is aqueous because those ions dissolve in water. Notice the distinction as well. The nitrate ion has a negative charge and it's labeled aqueous because it starts out being dissolved in that solution, and then it forms that toxic gas, either nitrogen monoxide or nitrogen dioxide, depending on the concentration. So here we have the reaction between the copper penny and the nitric acid. So we just replaced X with a specific metal here, copper. So our copper solid reacts with the nitrate to form this nitrogen monoxide gas, and then we have copper plus 2 ions. If you look at this reaction and you think about if you try to balance this reaction, if you look at the nitrogens, they're already balanced, and then the coppers are already balanced at 1 and 1 apiece. But on the oxygens, if we try to balance this, we have 3 oxygens on the left and only 1 on the right. So we would go and put a 3 there. But that leaves us with 3 nitrogens. So if we go back and put a 3 there, now we have 9 oxygens. And we would be playing this game back and forth all day, and it would never be balanced. So redox reactions must be balanced using a special method, and that method is called the half reaction method, and that's what we're going to work through here. We're going to skip several slides that have some information on them about specific redox reactions. We're going to skip these because previously on the AP exam you had to memorize what would happen to these ions. And now they're going to give us the starting, and they just need us to be able to tell who's oxidized, who's reduced, and of course we need to be able to balance it, which is what we're going to do here. To balance a redox reaction that's in acidic solution, we are going to do the following steps. The first thing is we need to separate it into 2 unbalanced half reactions. So we need to write the oxidation half and the reduction half separately. So we're going to be looking at 2 separate reactions. They're really going on at the same time, but we want to separate the oxidation from the reduction for the balancing. The next thing we'll do is for each of them, we're going to balance all of the atoms in the reaction except for oxygen and hydrogen. And then we'll come back to balancing those because those are going to be the most difficult. We'll balance the oxygens next by adding water molecules. If a reaction needs more oxygen or produces more oxygen, it can do so by using or producing water because all these reactions take place in water. So we'll just add water molecules as needed. These reactions also take place in acidic solution, and that means there's excess hydrogen ions. So if we need some more hydrogen on either side of the reaction, we'll just add H+ ions to balance the hydrogens. We will then look at our electrons and use those to balance any charge differential on each side. So on the oxidation reaction, we're going to be having electrons as a product because electrons are lost. So here they'll be on the product side. So I'll put a P there for product. And then on the reduction, we're gaining electrons, so we'll have electrons on the reactant side in that half reaction. So both of them will need electrons. The oxidation should need them on the product side, and the reduction should need them on the reactant side. So you remember RR, reduction, reactants. We'll then put the equations back together and cross-multiply to cancel the electrons and cancel anything else that may be the same in both reactions. Okay, so let's practice this with our copper reaction. First off, we need to separate it into the reduction and the oxidation, and that's going to require knowing who was oxidized and who's reduced. So as a refresher, to do that, we need our oxidation numbers. So here we have an element by itself, so that's an oxidation number of 0. Here's oxygen in the compound, and it's not peroxide, so that's -2. -2 times 3 is -6, and we've got to add up to -1. So what minus 6 would give us -1? That will be a 5. Over here, nitric oxide, -2 for oxygen. It's not peroxide, so nitrogen's got to be 2, so they can add up to 0. Here you have copper plus 2, and that's all it is, so its oxidation number is 2. So the question again is who was reduced for our reduction half reaction? The copper went from 0 to +2. That's not reduced, but the nitrogen went from 5 to 2, so that is reduced. So for our half reaction, we'll have nitrate goes to this NO. So we'll write that out as step 1. Step 2 is to balance all the elements except for oxygen and nitrogen, and oxygen and hydrogen. So you see here we have a nitrogen atom, so we need to make sure they're balanced. We have 1 on each side, so that's already done. So step 2 would be completed already. In step 3, we're going to balance oxygens by adding water. So if you look on the left-hand reactant side, we have 3 oxygens, and on the right-hand side, only 1. So to balance, we need 2 more oxygens, and to get 2 more oxygens, we'll add 2 water molecules. In step 4, we balance hydrogens by adding H+. On the left-hand side, we have no hydrogen, and on the right, we have 4 hydrogens in those 2 water molecules. So to balance, we'll add 4 H+ on the left-hand side. Step 5 is to add electrons to balance our charge. So let's look at our charges. Here we have a charge of -1, and then here we have 4 positive ones. So -1 and 4 positive ones, that's a total of +3. On the right-hand side, we have 0 as our charge on nitrogen monoxide and 0 as our charge on water. So our only charge is +3 on the left-hand side. What you've got to do is you've got to make the sides equal, and you're adding electrons. So electrons are negative, so you're going to add them to the highest side to make the charge come down. So currently we have a +3 on the left and a 0 on the right, so we need to make that +3 equal to 0. So we can do that by adding 3 electrons. You can add them anywhere on the reactant side, they just happen to add them right here before the arrow. Remember, this is your reduction half, so your electrons should be reactants. Okay, so we're done with the reduction half. Let's move on to the oxidation half. We said that nitrogen was oxidized, reduced, so copper must be the one that's oxidized. So that'll be copper solid goes to copper plus 2. In step 2, we need to balance any atoms that are not oxygen and hydrogen. So we have 1 copper on each side. That's already balanced. Step 3 is to balance oxygen by adding water, but there's not any oxygen. And step 4 is to balance hydrogen by adding H+, but there's no hydrogen, so we don't need to do that either. Now step 5, we need to balance our charge by adding electrons. On the left-hand side, we have copper solid with a charge of 0, and on the right, we have copper plus 2 with a charge of plus 2. We need to make them equal. So we need to make the copper plus 2 equal to 0. We can do that by adding 2 electrons. This is the oxidation half reaction, so our electrons should be products. So as you see, we put 2 electrons here, and that 2 plus and those 2 negative electrons are going to equal 0. And that's good that they're on the product side because this is the oxidation, meaning they're being lost. So we now have our 2 half reactions. We have our reduction half, which we balanced earlier, and you see it written there. And we have our oxidation half. The next step is to make sure that you gain the same number of electrons that you lose. So currently we have ourselves gaining 3 electrons in the reduction, but only losing 2 in the oxidation. So to remedy that, we're going to cross multiply. And what that means is we're going to multiply the reduction reaction by 2, because 3 times 2 is 6. And we'll multiply the oxidation half by 3, because 2 times 3 is 6. The goal here is just to make your electrons equal in the reduction and the oxidation. But you can't change your electrons without changing everything else in the reaction. So for the reduction half, we're going to multiply it by 2. So everything is getting multiplied by 2. And in the oxidation half, everything is getting multiplied by 3. So you see, we multiplied everything by 2. So we have 2 nitrates, 8 hydrogen ions, 6 electrons, 2 nitrogen monoxides, and 4 waters. So everything in the reduction got multiplied by 2 for the sole purpose of getting us 6 electrons. The copper oxidation half all got multiplied by 3, again, for the purpose of giving us 6 electrons. So there's 6 electrons in the reduction and 6 electrons in the oxidation, which is perfect because we can't create or destroy electrons. We have to exchange equal amounts. Now we can put these 2 half reactions together and cancel anything that we see on both sides. So here we are adding them together. The only thing I see in both reactions is electrons. 6 electrons on the left, 6 electrons on the right. So those should be able to cancel. Otherwise, we're just putting everything together. So all our reactants are going on the reactant side in any order. It doesn't really matter. And all our products are going on the product side, also in any order. That doesn't really matter. And we just want to make sure, double check that everything balances in the end. And this would be our balanced redox reaction. We'll skip this side, as well as this one, and this one, and this one, and this one, and this one. All right, moving on to one more balancing on example 2. So skip a few slides, catch up with me here. We are doing example 2, where we have an acidic solution containing tin-2-chloride that is mixed with potassium permanganate. And they want us to write a balanced chemical equation for this reaction. So we're going to start off with the net ionic equation. Now, most of the time, they're either going to give this to you, as you see here, or they'll be more specific in their words. Because in this reaction, chloride turns out to be a spectator. So we don't include that in our balanced equation. And then the potassium is also a spectator. So we're not including that in our balanced equation. You would not be able or required to predict the products here. Okay, they would have to give them to you. So from here, though, from this reaction here, we should be able to balance using the procedure that we just learned. So we're going to go through those steps again to balance this equation. How do you know that you need to do all these steps? Okay, one way is to try for just a second to balance it, and if it's super difficult, then it's probably a good idea to start using those steps. For example, in this one, there's 4 oxygen on the left and there's not any oxygens on the right. So that is a good clue that we might need to use our steps to balancing redox. Another clue though is if it says acidic or acidified solution, like you see here, that's a good clue. If you want to star this clue here, that's a good clue that you need the procedure to balance the reaction. Right, so this time we're going to start with the reduction half reaction. So who is reduced here? Let's use our oxidation numbers. Oxygen's -2, that makes -8. We've got to add up to -1. So what could this be to add up to -1? Must be a 7. 7 minus 8 would be -1. The rest of these are super easy. 10 is +2, manganese +2, 10 +4. Alright, so who was reduced? Manganese went from 7 to 2. That sounds like a lower number to me. So manganese was reduced. So we'll focus on this permanganate going to this manganese ion as our reduction half reaction. So set that up first. Our second step is to balance anything that is not an oxygen or a hydrogen. So on the left we have 1 manganese and on the right we also have 1. So those are already balanced. Next, we balance oxygen by adding water. 4 oxygens on the left, none on the right. So 4 waters would balance that. Next, we balance our hydrogens by adding H+, no hydrogens on the left, and 8 hydrogens in those 4 waters. So 8 hydrogen H+ on the left to balance those out. And finally, the part that most people find the most difficult, hopefully you're getting the swing of it though, that is your electrons. How many and where do they go? Well, it's the reduction half, so I'm guessing they're going to be reactants. But let's look at our charges. Got a -1 here and 8 positives. -1 and 8 positives. That makes 7 as our charge on this side. And on this side we have a +2. +2. The point of the electrons is to make these charges equal. And electrons are negative. So we're going to add them to the larger side to bring it down equal to the smaller side. So how many electrons would it take to make this 7 a 2? I don't want it to be a 0 because the other side isn't 0 and I want the sides to be equal. So the 7 to become a 2, that means I need 5 electrons, right? 7 minus 5 will give me 2. So I'm going to put in 5 electrons and you see them here. And that is the end of my reduction half reaction balancing. Alright, let's move on to the oxidation. So if manganese was reduced, that means the 10 must be oxidized, and it did go from 2 to 4, so that makes sense. So there's the half reaction for the oxidation, at least to start. Step 2, balance any atoms that aren't hydrogen or oxygen. We got 110 on the left, 110 on the right. So done. Step 3, balance oxygen by adding water. There are no oxygens. Step 4, balance hydrogen by adding H+. There are no hydrogens. And step 5, balance your charge by adding electrons. Well, where do they go and how many do we need? Let's check that out. So we've got a 2 charge on the left and a 4 charge on the right. And we want our charges to be equal. This is the oxidation half, which means my electrons should be products. But we'll see. Which one is larger, 2 or 4? 4 is larger, so I'm going to add electrons to bring it down to 2. How many electrons do we need to bring 4 down to 2? Well, I believe that would be 2 electrons. So let's put those on the product side. That 4 plus and those 2 minuses do equal +2, and that's the same thing as on the left. So we're done with step 5. Alright, now we're ready to look at how to put them together. So in the reduction half, we had 5 electrons that were being gained, and in the oxidation, only 2 were lost. So we've got to make this equal. So in order to make 5 and 2 equal, we can make them both 10, right? So we'll multiply the top reaction by 2, that would make that 10 electrons, and we'll multiply the bottom one by 5. Remember when you do that to multiply everything. There we go. There's our multiplication of the top and the bottom. So we have our reduction half now and our oxidation half, and we're ready to put them together finally. So there they are. You'll see on the left and the right that your 10 electrons cancel. If your electrons don't cancel, then we've got to go back and figure out what went wrong. But luckily here we have 10 on the left, 10 on the right, they're gone. Put all your other reactants on the left, all your other products on the right, and that gives you your balanced redox reaction. All right, so make sure that you are very, very familiar with those steps. Hopefully you can memorize them, and then ready to practice balancing redox reactions in acidic solution. The method that we looked at in these 2 examples, it will work for any redox reaction. If there's not water or hydrogen in the balanced equation, it's because it may have canceled from your half reactions, or there may have been no hydrogen or oxygen involved, so you may have not needed it. Sometimes, though, you will have hydrogen and oxygen in the half reactions, and then they'll cancel out when you put those together. An example problem from the AP exam, they could give you a redox reaction and ask you to write the half reactions and balance them, or they could give you the whole thing and ask you to balance. It's a really popular multiple choice question. They'll give you the equation and then they'll ask you, like, what is the coefficient on water, for example. And it's hard for people because they don't recognize they need to use the steps, and they just try to balance it using our traditional methods, and they keep getting stuck, and it turns into a point of frustration. So we'll have to keep this in mind as we move forward when we see redox reactions. If they stump us at first, let's turn and use these steps to try to balance. So we'll pick up here with this example problem in the next video.